Welcome to This Explainer. Today we're going on a mission to completely eliminate one of the absolute most annoying problems in all of science and math. You see, when we're actually out there studying the universe, we're not just dealing with comfortable everyday numbers, right? We're dealing with the extreme edges of reality. And doing that, well, it requires a very specific mathematical tool to keep things from turning into a total mess.
Okay, check this out. 150 billion, 150,000 million, billion. That is the distance from the Earth to the Sun, in meters. I mean, look at all those zeros. When you're a scientist or a mathematician, having to write this out over and over and over again or punch it into a calculator, the risk of human error is literally off the charts. You miss one single zero or, accidentally add an extra one, and suddenly your calculations are completely ruined. It's frustrating, it's messy, and honestly, it's just way too easy to make a massive mistake when you're forced to sit there and count every single zero manually.
But let's slow down for just a second here, because the exact same frustrating problem happens on the complete opposite end of the scale. Imagine trying to write down the tiny, infinitesimal mass of a single atom, or say, the weight of a microscopic virus. You'd be writing a decimal point followed by just a seemingly endless string of zeros before you finally hit a number that actually means something. So whether things are massively huge or microscopically tiny, standard numbers just kind of fail us. We desperately need a standardized mathematical fix to abbreviate these crazy extremes.
Section 1. The Ultimate Life Hack. Introducing Scientific Notation.
Okay, let's dive into this. Scientific notation is essentially the hero of our story. It's a brilliant, standardized system designed by mathematicians to safely and efficiently abbreviate the extremes of our universe. It takes all that messy zero counting and condenses it down into something clean, elegant, and pretty much foolproof. Here is the algebraic cheat code for the whole thing. A times 10 to the power of n. Every single number written in scientific notation takes this exact form. You're basically taking a nice manageable number, that's our a, and multiplying it by a power of 10, that's our 10 to the n. This one simple formula lets you express literally any size imaginable without writing a single useless zero.
Now, for this beautiful system to actually work, there are some pretty strict conditions. You absolutely must follow these two golden rules. First, that base number a, it has to be exactly between 1 and 10, meaning it can be exactly 1, but it must be strictly less than 10. It can be positive, it can be negative, but its absolute value has to sit right in that sweet spot. Second rule, the exponent n must be a whole integer. It can be positive, negative, or even 0, but absolutely no fractions and no decimals up there in the exponent. These aren't just suggestions, they're mandatory conditions. Break them, and the whole system falls apart. But stick to them, and you're golden.
Section 2. The Training Montage. Converting to Scientific Notation.
All right, time for some action. Let's start with large numbers, using 450,000 as our prime example. How do we actually shrink this down safely? Well, step 1, you've got to find the hidden decimal point. For whole numbers, it's always hiding way over on the far right. Now, I want you to physically imagine grabbing that decimal, and we're going to slide it to the left, step by step. Ready? 1, 2, 3, 4, 5 spaces. We slam the brakes the moment we hit a number between 1 and 10, which gives us exactly 4.5. Now, since we moved that decimal 5 spaces to the left, our exponent becomes a positive 5. So our final wonderfully clean result is 4.5 times 10 to the power of 5.
But what about those tiny microscopic numbers? Let's take 0.00032. This time, we've got to go the opposite way. We grab that decimal and slide it to the right until we land right after that very first non-zero digit. So we go 1, 2, 3, 4 spaces to the right, which gives us 3.2. Now, because we moved to the right to handle a tiny fractional value, our exponent becomes negative. 4 spaces right, that means an exponent of negative 4. So our final result here is 3.2 times 10 to the power of negative 4.
Section 3. Reverse engineering back to standard form.
True mathematical mastery means you can confidently unpack these notations right back into their original standard form. And to do that, you really just follow the signs. And this brilliantly illustrates the whole concept. If you have a positive exponent, like the 3 in 6.12 times 10 to the third, it means the underlying number is large. So to expand it, you just move the decimal right by 3 steps to let it grow, giving you 6,120. But if you have a negative exponent, like the negative 2 in 7.5 times 10 to the negative second, the underlying number is small. You move the decimal left by 2 steps to shrink it, filling in any empty spaces with zeros, and you get 0.075. So just remember this visual anchor. Positive means grow to the right, negative means shrink to the left.
Section 4. The final boss, surviving the exam trap.
Okay, before we wrap up, as your guide here, I really need to warn you about a classic algebraic trap. Teachers absolutely love to throw this specific trick on exams to see if you're truly paying attention to those golden rules or if you're just sort of cruising on autopilot. So look at this. Is 45 times 10 to the power of 3 written in correct scientific notation? Take a second. What do you think?
No, it is absolutely not. And what's actually super interesting here is just how sneaky this trap is. I mean, at a quick glance, it totally looks like scientific notation, right? But wait, 45 blatantly violates our very first golden rule. Remember, the base number has to be strictly less than 10. So to fix this, we have to correct that base by dividing 45 by 10, shrinking it down into 4.5. But to keep the whole mathematical equation perfectly balanced, since we shrank the base by 1 decimal place, we have to grow the exponent by 1. So we add 1 to that exponent of 3, making it a 4. The true, correct, standardized form is 4.5 times 10 to the power 4. Always, always double-check your base number.
By understanding how to spot those tricky little traps and gracefully shift those decimals back and forth, you've just unlocked a major skill. Because math isn't just about blindly following rules, is it? It's about having the exact right tools to explore the extremes of our universe. You now have the literal superpower required to effortlessly quantify the absolute largest galaxies and the absolute smallest particles in existence, all without ever getting lost in a sea of zeros.
Which brings us to our final thought for this explainer. Now that you are officially armed with scientific notation, I want you to think about that incredible microscopic world all around us. So, how many negative exponent zeros do you think you would actually need to write down the exact mass of a single invisible virus? It's a pretty staggering thought. And the best part is, it's one that you're now mathematically equipped to handle and explore completely on your own. Keep questioning, keep practicing, and hey, thanks so much for exploring this with me today.